MSE 302, Chapter 1, Tensile Response of Materials. Chapter 1, Tensile Response of Materials. The tensile test is the experimental test method most widely employed to characterize the mechanical properties of materials. From any complete test record, one can obtain important information concerning the material's elastic properties, the character and the extent of plastic deformation, yield, and tensile strength and toughness. That so much information can be obtained from one test justifies its extensive use in engineering material research. To provide a framework for the varied responses of tensile loading in load-bearing materials, several stress-strain plots reflecting different deformation characteristics will be introduced in this chapter. 1.1. A definition of stress and strain. Before discussing engineering material stress-strain response, it is appropriate to define the terms stress and strain. This may be done in two generally accepted forms. The first definitions, used extensively in engineering practice, are 1.1 A and B, engineering stress and engineering strain. Engineering stress is a load, an initial cross-sectional area. Strain is a change in length over initial length. Alternatively, stress and strain may be defined by equation 1-2 and A and B, true stress and true strain. The fundamental distinction concerning the definitions for true stress and strain is recognition of the interrelation between gauge length and diameter changes associated with plastic deformation. That is, since plastic deformation is a constant volume process such that equation 1-3 holds, any extension of the original gauge length would produce a corresponding contraction of the gauge diameter. For example, if a 25 mm 1-inch log sample were to extend uniformly by 2.5 mm owing to a tensile load P, the real or true stress would have to be higher than that computed by the engineering stress formulation. Since L2 over L1 is equal to 1.1, from equation 1-3, A1 over A2 is 1.1, so that A2 is equal to A1 divided by 1.1, the true stress is then shown to be the following, and is larger than the engineering value. By combining equations 1-1A, 1-2A, and 1-3, the relationship between true and engineering stress is shown to be 1-4. By combining equations 1-1B and 1-2B, true and engineering strains may be related by equation 1-5. The need to define true strain as in equation 1-4 stems from the fact that the actual strain at any given time depends on the instantaneous gauge length, L sub I. Consequently, a fixed delta L displacement will result in a decreasing amount of incremental strain, since the gauge length at any given time, L sub I, will increase with each individual delta L increment. Furthermore, it should be possible to define the strain given to the rod by considering the total change in length of the rod as having taken place in either one step or any number of discrete steps. Stated mathematically, sigma of epsilon sub n is equal to epsilon sub t. As a simple example, take the case of a wire drawn in two steps with an intermediate annealing treatment. On the basis of engineering strain, the two deformation strains would be L1 minus L initial divided by L initial, and L2 minus L1 divided by L1. Adding these two increments does not yield a final strain of L2 minus L0 divided by L0. On the other hand, a summation of true strains does lead to the correct results. Therefore, we have the following equation. Example 1.1, we will come back to it later. The use of true strains offers an additional convenience when considering a constant volume plastic deformation process, in that epsilon sub x plus epsilon sub y plus epsilon sub c is equal to 0. In contrast, if we find a less convenient relationship, 1 plus epsilon x times 1 plus epsilon y times 1 plus epsilon z is equal to 1, for the case of engineering strains, this is a less convenient relationship. 1.2 Stress-strain curves. 1.2.1 Elastic response, type 1. We will also talk about 1.2.1.1 Generalized Hooke's law. I will also be talking about 1.2.1.2 resiliency, 1.2.1 elastic response type 1. Over 300 years ago, Robert Hooke reported in his classic paper of spring the following observations. Take a wire string of 20 or 30 or 40 feet long and fasten the upper part. To a nail and to the other end fasten a scale to receive the weights. Then, with a pair of compasses, measure the distance from the bottom of the scale to the ground or floor beneath. Then put the weights into the scale and measure the several stretchings of the said string and set them down. Then, compare the several stretchings of the string, and you will find that they will always bear the same proportions one to the other that the weights do that made them. This observation may be described mathematically by the equation for an elastic spring, equation 1-6, where F is equal to applied force, X is equal to associated displacement, K is equal to proportionality factor, often referred to as the spring constant. When the force acts on a cross-sectional area A, and the displacement X related to some reference gauge length L, equation 1-6 may be written as equation 1-7. Where sigma is equal to stress, epsilon is equal to strain, E is equal to proportionality constant, often referred to as Young's modulus or the modulus of elasticity. Equation 1-7, called Hooke's law, describes a material condition where stresses and strains are proportional to one another, leading to a stress-strain response shown in figure 1.1. A wide range of values of the modulus of elasticity for many materials is shown in table 1.1. The major reason for these large property variations is related to differences in the strength of the interatomic forces between adjacent atoms or ions. To illustrate the fact, let us consider how the potential energy E between two adjacent particles changes with their distance of separation x, figure 1.2a. The equilibrium of distance of particle separation, x naught, corresponds to a minimum in potential energy. This is associated with a balance of the energies of repulsion and attraction between two adjacent atoms or ions. The form of this relationship is given by E equals negative alpha divided by x to the power of m plus beta divided by x to the power of n, where the two negative alpha divided by x to the power of m and beta divided by x to the power of n correspond to the energies of attraction and repulsion, respectively, and n is greater than m. At x naught, the force acting on the particles is equal to 0, figure 1.2b. The first derivative of the force with respect to distance of particle separation, df over dx, then describes the stiffness or relative resistance to separation of the two particles, such as df over dx is analogous to the Young's modulus quantity given in equation 1-7. A simple analysis of bonding forces shows that the elastic stiffness is proportional to 1 divided by x naught to the power of n. Examples of the strong dependence of elastic stiffness on x naught for alkali metals are shown in figure 1.2c. From the above discussion, it follows that values of E same value in table 1.4 for E of 111 and E of 100. For iron, we have this expression, E of 110 is equal to 210.5 gigapascals. No idea where we're getting that from. We have some other things that would be good to look at. Example, note that E111 is greater than E110 is greater than E100, and that E110 is in good arrangement with the average value of E, modulus Young's elasticity, for the polycrystalline sample, table 1-1. For the case of tungsten and any other isotropic material, then we have equation 1-15. If we compare equations 1-15 with equation 1-10, the elastic constants S sub ij may be described in terms of the familiar strengths of material elastic constants. Therefore, equation 1-16 A, B, C. Finally, from equation 1-16, we have the following expression, and we have equation 1-16b. For the case of hexagonal crystals, the matrix in equation 1-11 reduces to equation 1-17, where L sub 1, L sub 2, L sub 3 are direction cosines for directions in the hexagonal unit cell. From equation 1-17, note that in hexagonal crystals E depends only on the direction cosine L sub 3, which lies normal to the basal plane. Consequently, the modulus of elasticity in hexagonal crystals is isotropic everywhere in the basal plane. 1.2.1.2 Resiliency. The resilience of a material is the measure of the amount of energy that can be absorbed under elastic loading conditions, and which is released completely when the loads are removed. From this definition, resilience may be measured from the area under the curve in figure 1.1. Equation 1-18, where sigma sub max is the maximum stress for elastic conditions. Epsilon sub max is the elastic strain limit. From equation 1-7, we have equation 1-19. Should an engineering design require a material that allows only for elastic response with large energy absorption, such as in the case of a mechanical spring, the appropriate material to choose would be one possessing a very high yield strength with low modulus of elasticity. 1.2.2 Elastic homogeneous plastic response type 2. When a material has the capacity for plastic deformation, irreversible flow, the stress-strain curve often assumes the shape of curve 2, figure 1.2. Here we see the same elastic region at small strains, but now find a smooth parabolic portion of the curve, which is associated with homogeneous plastic deformation processes, such as the irreversible movement of dislocations in metals, ceramics, and crystalline polymers, and a number of possible deformation mechanisms in amorphous polymers. That the curve continues to rise to a maximum stress level reflects the increasing resistance on the part of the material to further plastic deformation, a process known as strain hardening. The portion of the true stress-strain curve from the onset of the yielding to the maximum load may be described empirically by the relationship generally attributed to Hallam. Equation 1-20, where sigma is the true stress, epsilon is the true plastic strain, n is the strain hardening coefficient, k is the material constant, defined as the true stress at a true strain of 1. However, Bulfinger proposed a similar parabolic relationship between stress and strain almost 200 years earlier. The magnitude of the strain hardening coefficient reflects the ability of the material to resist further deformation, and may be equal to unity, which represents ideally elastic behavior, or equal to 0, which represents an ideally plastic material. Selected values of strain hardening coefficients for some engineering metal alloys are given in table 1.5. Note that n values are sensitive to thermomechanical treatment. They are generally larger for materials in the annealed conditions and smaller for the cold work state. Such data may be derived by plotting true stress and associated true strain values on log-log paper. If equation 1-20 was absolutely correct, a straight line would result with a slope equal to n. However, this is found not always to be the case, and reflects the fact that this relationship is only an empirical approximation. When a nonlinear log-log plot does result from a given material, the strain hardening coefficient is often defined at a particular strain value. In general, n increases with decreasing strength level and with decreasing mobility of certain dislocations in the crystalline lattice. More will be said about this material property in Chapter 3. 1.2.2.1 Strength level in materials. It has become common practice to define several strength levels that characterize the material's tensile response. The proportional limit is that the stress level below which stress is proportional to strain, according to equation 1-7. Remember, equation 1-7 is important. The elastic limit defines the stress level below which the deformation strains are fully reversible. In most engineering materials, these two quantities are essentially equal. However, it is possible for a metal to exhibit nonlinear but elastic behavior. For example, very high-strength filamentary particles, often called whiskers, can exhibit elastic strains in excess of 2%. In this range of very large elastic strains, the modulus of elasticity reveals its weak dependence on strain, something that is completely obscured when strains are very small. For example, note that dF divided by dx in figure 1.2b decreases with increasing distance of particle separation. As such, Hooke's law, equation 1-7, represents an empirical relationship, albeit a good one at small strains. Consequently, the elastic limit is approximately equal to the proportional limit and may be slightly higher in some cases. A much more important material property is the yield strength, a stress level related to the onset of irreversible plastic deformation. This quantity is difficult to define, since the point where plastic flow will depend on the sensitivity of the displacement transducer. The more sensitive the gauge, the lower the stress level where the plastic flow is found. In recent years, special capacitance strain gauges have been used to measure strains in the range of 10 to the -6. In fact, a number of studies dealing with the mechanical behavior of materials in the microstrain region have been undertaken as a result of this breakthrough in instrumentation. These investigations have shown, for example, that plastic deformation, the irreversible movement of dislocations, occurs at stress levels many times lower than the conventionally determined engineering yield strength. To arrive at a uniformly accepted method for determination of the yield strength, therefore a standard test procedure, ASTM standard, has been adopted. The yield strength value is obtained in the following manner. 1. Determine the engineering stress-strain curve, such as the one in figure 1.6. 2. Construct a line parallel to the elastic portion of the stress-strain curve, sigma-epsilon curve, but onset from the origin by a certain amount. The generally accepted offset is 0.002 or 2% strain. And 3. Define the yield strength at the intersection of the stress-strain curve and the offset line. As cited above, this value is usually defined as the 0.2% offset yield strength. The ultimate tensile strength is defined as the maximum load divided by the initial cross-sectional area, while the true fracture stress is the load at fracture divided by the final cross-sectional area with correction made for any localized deformation, necking, in the final fracture region. A compilation of tensile properties for a number of engineering materials is given in tables 1.6 and 1.7.